All right. Hello, everyone. It's finally time for class to start. There's no one here yet, so I'm not asking if anybody has any questions, but obviously, when you get here, you're welcome to ask questions. I'm just going to begin picking up where we left off. The last video I posted, which by the way, I had to delay because it took a lot of editing, so it only became visible like about 5 minutes ago, and even then is still another scene that I've got to put in it. There was a little screw up when one of my students was in there that day. When he left, I got a little discombobulated because I changed what I was going to cover at the last second and tried to do it on the fly and ended up making some mistakes and not specifying the problem as appropriately as I needed to. So what I've done is I've written up a version of the statement of the question of a coaxial cable, and I'm trying to input a photo of that particular question just before I work the problem. Even though in the problem I have the wording that's not all that correct, it's missing some key points like the fact that the coaxial cables were infinitely long, that their charge per unit length was lambda, also that the small radius was r sub zero, not just plain r, because I needed r as a variable, and the big radius was actually big R, but that part I did have right. So, anyways, that's what you'll see once you get about halfway through the video. Well, I guess it's around right around the 1 hour mark is when the student had to leave. So somewhere in there you'll run into it. But that should be posted now on my YouTube channel, and I'm going to go ahead and start talking in this video about chapter 24 as well. So again, we're in chapter 24 being the chapter called Capacitance, Dielectric, and Energy Storage. And the last time we met, I actually used the time to do what I call this three-step paradigm that I expect all my 242 students to be able to accomplish. And that is basically, can you use Gauss's law or even Coulomb's law to calculate the electric field between two parts of a parallel plate or of a capacitor, period, not just a parallel plate capacitor. And then step two, can you use delta V equals the negative integral of E dot dl to calculate the voltage difference between the positive part and the negative part of the capacitor. And then step three was use C equals Q over V to calculate the actual capacitance. So I did that yesterday using a parallel plate capacitor, which we started off using Gauss's law to calculate the electric field created by an infinitely large, uniformly charged plate, conducting plate. And we used Gauss's law to calculate that. Then I used the idea of putting a positive one next to a negative one, calculated what the electric field would be between the two plates, what the electric field would be on the left side of the plates, what the electric field would be on the right side of the plates. And then I used delta V equals negative integral E dot dl to calculate the voltage difference between the negative plate. In other words, I did the path integral from the negative plate to the positive plate so that I would get a positive voltage. And then I took C equals Q over V and divided the Q by the V, and that gave me a capacitance, which is always supposed to be a geometrical calculation. It should never have a lambda, a sigma, uh, a rho, charge densities. It should never have any charges in it. It should never have any charge densities in it or anything like that. It should all be geometric. And that's ultimately what we found out. In fact, we calculated that C turned out to be epsilon zero times A over D. I even mentioned that if you add a dielectric in there that has a dielectric constant K, then the capacitance will become K times epsilon zero A over D. But I also mentioned that that K times epsilon zero turns out to be what we normally just call epsilon for the dielectric. So you can also say that the parallel plate capacitor with a dielectric in it has a capacitance C equals epsilon, notice without the sub-zero, A over D. So we did that. Then we did a coaxial cable in which we calculated the capacitance for that one. And that one turned out to be, I think, 2 pi epsilon naught over the ln of big R divided by little r zero. So, anyways, that was what it was. Now I'm going to start off again in chapter 24, and I have one more example, or maybe two more examples that I really wanted to do with regards to using Gauss's law and Coulomb's law and all that good stuff. Well, not Coulomb's law necessarily, but Gauss's law to calculate the capacitance. And that is, for instance, a spherical conductor. So let me go ahead and start off with that by imagining a spherical conductor, and we'll use Gauss's law, step one of the paradigm. Use delta V equals the negative integral E dot dl, step two of the paradigm, and then C equals Q over V, step three of the paradigm, to calculate the capacitance of a spherical capacitor. So let's go ahead and start with that right now. I'm going to do so by sharing my iPad screen, and that should come up any minute now. And great, my allergies are kicking in. So that's always helpful. Okay, that looks like it's coming up now, so hopefully we should see it in a second. So what we want to do here is we'd like to calculate the capacitance of a spherical capacitor. So a spherical capacitor basically consists of two concentric spheres. I'm going to make two concentric spherical shells, and the two concentric spherical shells will have a radius. Let me just draw it. That'd probably be the easiest way. So I'm going to go ahead and draw one of the spheres. So it has basically a inner sphere, and that sphere has a radius of r sub a, and then it has and that technically, by the way, is a inner spherical shell. So I'll just leave it like this, even though the details of it being an inner shell versus an outer shell versus a solid shell doesn't really matter too much. But now I'm going to take that's a spherical shell as the inner terminal, and then there's another spherical shell, and I'm trying to make it a decent looking circle, so I'm marking off dots so I can use my automatic drawing tool that will make it an actual circle despite how badly I miss drawing the circle. Let's see if that works. That's not too bad, not perfect, but not bad either. Now I just stretch it a little bit, make sure it hits the right sizes, and that does seem to be pretty well centered. Now what I'm going to do is make the outer shell of that one as well. So I'm going to go half a mark beyond each of those spots and try to draw another circle. Well, that is not going well, is it? Nope, that was not well, but I might still be able to move it to where it looks like it. Oh, I'm trying to move, not change. There you go. So now if I can just center that up, then it will be good. Okay, so that's cool. So just in terms of my radiuses that I was talking about, I'm going to have this radius be r sub a, and this radius be r sub b. That's the two radii, and those are the only ones that we care about. In fact, I am going to imagine that the inner shell has a charge of positive q. So we'll say plus, 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 and then we'll say minus, 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 and I'll try to again show it as uniform as I possibly can. This inner surface is going to have a charge negative q, and this outer surface is going to have a charge positive q. And what I want to calculate again is the capacitance. So I'm going to say, what is the capacitance of the concentric conducting shells? So that's really the question. Now, what we're going to do is try to use the three-step paradigm to work it out. So let's start off with solution. So the solution is going to require us to use C equals Q over V. In order to get V, we're going to have to use delta V equals, we normally write it as V final minus V initial, is equal to the negative integral of E dot dl. And then, in addition to that, we can't actually calculate that delta V, which is the V that goes in the denominator, unless we have the electric field. So we're going to use Coulomb, or excuse me, Gauss's law, the closed integral of E dot dA is equal to Q enclosed over epsilon naught. We're going to use that to calculate the electric field. So step one will be use Gauss's law. Step two will be use delta V equals negative integral of E dot dL. And step three is going to be use C equals Q over V. So this is what we're trying to do. This is not unlike an example that your book has in it. I want to say it was example three, but I'm just going to call it example. Okay. So that's our example. This is what we're working as the first problem in the 242 class for today. So let us begin. I'm going to draw a Gaussian surface. That Gaussian surface is going to be, let's say, green. And what I'm going to do is I'm going to imagine it being a sphere of radius smaller than RB but bigger than RA. So I'm roughly doing this. Now I'm going to attempt to draw a nice circle to represent the sphere that I'm referring to. And that's it. So this is our Gaussian surface. Actually, that last part of the drawing was supposed to show it having a three-dimensional shape, but because it was on the auto tool made it look kind of crappy. So now it looks okay. I could also do like this. And again, that just shows a little bit more how it's spherical. I didn't like how that last one turned out. All right, so now that we have the Gaussian surface in there, I'm going to label that. And it is a sphere, so I'm going to put sphere on here so it won't be confused as a circle. And now I'm going to go ahead and write left-hand side of Gauss's law. And of course, in order to do that, I have to have a hypothesis of my electric field. And my electric field hypothesis is E is going to be equal to E of R, meaning I think it's only going to depend on the distance from the origin, because what I'm imagining here is I'm imagining the center of the Gaussian surface as well as the center of the inner shell and the center of the outer shell are all at the origin of coordinates, so that we could, for instance, draw an x-axis pointing out this way. We can draw a y-axis pointing out this way and a z-axis pointing up that way. And then E of R means that the electric field depends only on the distance from the center of the circle that we are, and it will point in the radial direction R hat. Oops, I'm still in black there. Sorry about that. It'll point in the radial direction R hat. That's the radial direction that we recognize in spherical coordinates, which basically for any point in space that you're at, you imagine a line connecting that point in space back to the origin, and R hat will be parallel to that, but pointing from the origin towards the point. Okay, so that's what E of R is. I can even state that E of R technically has a I hat component or an X component of cosine phi, cosine theta. It has a Y component of cosine phi sine theta, and it has a Z component of just sine phi, where phi is the polar angle and theta is the actual azimuthal angle that is measured counterclockwise from the positive x-axis towards the positive y-axis. Okay, so that's just the explanation of all those details. Again, you don't really have to know these new coordinate systems. It just gives us a nice set of symbols that we can use. So the left-hand side of Gauss's law is the closed integral of E dot dA. And luckily, when you're using a sphere, remember there's only three symmetries that you can use to extract the electric field out of the integrand of Gauss's law. And those three symmetries are an infinite plane. And for that one, you use a Gaussian pillbox, and the top and bottom become very important, but the soup label is irrelevant. And then there's a infinite cylinder, and again, you use a Gaussian pillbox for that. But in this case, the top and bottom of the soup can is irrelevant, but the soup label is relevant. And then the third symmetry that you can use for Gauss's law is spherical symmetry. And then when you're using that, then the Gaussian surface is a sphere, and it doesn't have parts, so you really just have one integral. The actual integral in this case is therefore going to be the integral of e, oops, no vector symbol here, e of r hat, dotted with dA. That's the spherical dA for a little spherical window on the surface of the sphere, and it points radially outward as well. So dA r hat. Now, again, this is not something you really have to worry about when you're doing Gauss's law. The whole point of Gauss's law, when you're using it to solve for the electric field, as we're doing here in this weird, tricky way, the left-hand side is always just supposed to become an area times the electric field, and you choose the Gaussian surface such that the electric field is a constant on it. We know that the electric field should, by symmetry, only depend on the radial distance from the center of the sphere to wherever the point in space is, assuming that you're at least outside of one of the charges. We are considering radiuses between RA and RB, so clearly you are outside of the charged surface, so you have some charge inside. Now, if you actually wanted to know all the details, the dA would be R cosine phi times r cosine phi times d theta, and then it would be also times r d phi. So that's actually what your dA would be. Again, you don't have to know it. Really, what's going to happen here is the E of r, since it's on the Gaussian surface that we chose, it is a constant on the Gaussian surface. So the left-hand side becomes E of r, the magnitude, because that's completely a constant. And we use the linearity of the dot product to pull the dA through. So we end up having the integral of a differential surface area element of a spherical surface integrated. So obviously, when you integrate a differential area element on the surface of a sphere, you get the area, surface area of a sphere. Of course, it also has after it the r hat dot r hat, where we had pulled the dA through. But r hat dot r hat, each of those are unit vectors, so their magnitude is each one. And then the cosine of the angle between them is the cosine of 0 degrees because they're identical vectors. So the r hat dot r hat just becomes 1, and we basically just get E of r times 4 pi r squared, where again r is the radius of the Gaussian surface. So r is radius. So now we have the left-hand side. The right-hand side, as always, is Q enclosed over epsilon naught. So we say right-hand side is Q enclosed over epsilon naught. The Q enclosed is all the charge that's inside. We see if we take any radius that is even slightly bigger than RA, and definitely smaller than RB, will automatically have the total charge positive Q inside. So that's just going to be a positive Q over epsilon naught for the right hand side. Now we can set left hand side equal to right hand side. And when we do that, we get E of r times 4 pi r squared is equal to Q over epsilon naught. Again, I'm not writing that very big because ideally I'd like to fit this whole thing in there in this one page. So hopefully you can trace out what I'm doing here. In case there's any ambiguity, I'm going to mark off the segment so you won't think that lines are for different parts. So I just block that off. So now from the left-hand side equal to right-hand side, I can solve for E of R. And obviously we get Q over 4 pi epsilon naught R squared. And using our original hypothesis, that means the electric field E is equal to Q over 4 pi epsilon naught R squared, and it all points in the R hat direction. And that is for R between RA and RB. So we now have the electric field. That is step one. Now we can go ahead with step two. So with step two, what we're going to say here is, and I don't know why that keeps coming up here, sorry. With step two, I'm going to say delta V equals the negative integral of E dot dl. Okay, so what I'm going to do is I am going to actually integrate from RB to RA. So let's say from RB to RA. And the reason why I'm doing that is because the inner sphere is going to be the positively charged one, and that would normally be connected to, of course, the positive side of the power supply if you were making it. Charging it up, and therefore, if I go final minus initial, the voltage in the final will be larger than the voltage in the initial, so the delta V will come out to be positive, which is what I'd like to put under the Q in C equals Q over V. So I usually use this as a check to make sure I'm doing my line integrals correctly and all that good stuff. So here's the calculation. Delta V from RB to RA is going to equal the negative integral. Now I'm going to plug in my electric field, which is Q over 4 pi epsilon naught R squared, all of that times R hat. And now, as I've told you before, when we're doing this line slash path integral to compute a voltage change, that's technically a line integral or a path integral. And the trick to doing that, whenever you're doing a line integral or a path integral or even a surface integral, is you've got to make sure the integrand is evaluated on the line or the path, or in the case of a surface integral, on the surface. So for instance, if you're integrating along a path, for instance, y equals x squared, if you took all the y values that popped up in your integrand and replaced them with x squared, that would be a way of going about making sure that the integrand has been evaluated on the path. In this case, it's a little less complicated, but it's also a little more complicated. It's a little less complicated in that you don't have to follow a equation in y and x, but it's a little more complicated in that I'm not even going to state the equation, but basically I am going to follow a path that will be a radial path from the radius equal to RB into the radius being equal to RA. And you could imagine, for instance, me doing that along the y-axis or along the z-axis or along the x-axis. It doesn't matter. And in fact, because the electric field is a conservative field, any path will give you the right answer. But you can just imagine it as if it's going along the y-axis, if that makes you feel better. In this case, I'm going to say we're actually going along a line of basically R. So we're imagining a line in space that runs from the origin to maybe infinity. And we're going to get on that line and we're going to start at a radius RB and then integrate towards the center of the origins to RA. So in that case, I'm going to say let's let our DL dictate which way I'm going. So I'm going to put a negative in front of it because it's going to point in the negative R hat direction. And then the DL part just becomes DR. And then the vector part is indicated by the R hat. So that's what I'm actually integrating. And now that I've chosen to use the DL to indicate the direction in which I'm integrating, the range of integration just needs to go from small variable value to large variable value. The small variable value is, of course, r sub a, and the large variable value is r sub b. So that's my whole path integral, or line integral. You can see that the two negatives would cancel each other out, giving us a positive. You can also see that q over 4 pi epsilon naught are all constants. So what I'm going to get is positive q over 4 pi epsilon naught coming out in front of the integral. I'm integrating from RA to RB, and now I have dr over r squared is the integral that we're computing. So that's dr times r to the negative 2, for instance, is a nice way of thinking about it. I have made use of the linearity of the dot product by pulling the dr past the dot product, and after that comes r hat. Oops, it's in the automatic draw program. Sorry about that. So after that becomes the r hat dot r hat. So now you can see that's actually really badly drawn. So after the integrand becomes another part of the integrand, which is r hat dot r hat, which again we know is just 1. Now the integral of r to the negative 2 is 1 over negative 2, or excuse me, 1 over negative 1 times r to the negative 1. So this is going to be, in fact, negative q over 4 pi epsilon naught times 1 over r, but the 1 over r will be evaluated first at RB and then at RA. So it's going to be 1 over RB minus 1 over RA. Now, you know RB is bigger than RA, so 1 over RB is smaller than 1 over RA. So this quantity inside the brackets is negative, and then the negative sign in front of it makes it positive. So I'm just going to write it in the other order so that we'll know that it's positive. So what I'm going to have now is q over 4 pi epsilon naught 1 over RA minus 1 over RB, and that is the voltage difference. We can, in fact, if we wish, go ahead and get a common denominator. If we wanted to do that, which I'm going to, all we have to do is multiply the first fraction by RB over RB and multiply the second fraction by RA over RA. So then we'd get Q over 4 pi epsilon naught times, now it's going to be RA minus RB, or excuse me, RB minus RA. It's going to be RB minus RA over RA times RB. So that's what happened when we got the common denominator by multiplying the first fraction, which is 1 over RA, by RB over RB. That gave me RB over RA RB. And then the second fraction we multiplied by RA over RA, so that gave me RA over RA minus, I mean, RA times RB. So that's why I got RB minus RA in the numerator. Now that we have that, well, we've completed step 2, and that leads us to step 3. So step 3 is to apply C equals Q over V. And that's straightforward enough. We can see that C is equal to Q, and then I divide by the V. The V is Q over 4 pi epsilon naught times RB minus RA over RA RB. And that is the formula. It's not in the cleanest form, but for instance, you notice you have a fraction under the fraction bar. Division by a fraction is the same thing as multiplication by the reciprocal. So what I'm going to do is pull that q over 4 pi epsilon naught out and write it as 4 pi epsilon naught over q multiplied by q over the stuff in the bracket. Clearly the q's will cancel out, which I told you capacitance should never depend on anything related to charge. It should only depend on geometry. So when I do that, the 4 pi epsilon naught becomes part of the numerator, but so does the RA times RB. So 4 pi epsilon naught RA RB is the numerator, and the denominator turns out to just be RB minus RA. So we now have the complete formula for the capacitance of this spherical capacitor, and that is C is equal to 4 pi epsilon naught RA over RB minus RA, like that. And that is our answer. So normally I would ask if anybody has any questions or any thing they didn't understand about this. You, of course, can always put any questions in the at the base of the video in my YouTube channel, and I will get to it if you ask it, or I might actually just make up a new video to help you understand it. So, anyways, that's another one of the paradigms that I asked you guys to be able to do to basically be able to pass 242. You should be able to pull this off if you want to pass 242. There's going to be another paradigm later once we learn about the magnetic fields. In that case, you could use the law of Biot-Savart or Ampere's law to calculate the magnetic field, and then you could use basically a definition of inductance that we'll learn later, and you'll use the definition of flux, which is the integral of magnetic field dotted with dA, and you can use that with the formula for the induction and calculate the inductance in another three-step paradigm. So that's something that's to come. But anyways, this covers that. There is another example in your book where they use basically what used to be an old style antenna wire, which was, you could sort of imagine it being like a flat ribbon or a flat wide shoestring, for instance, made out of hard plastic, movable, bendable plastic, but still pretty rigid plastic. And then at each edge of the shoestring, if you will actually be a conducting wire inside of it. So you've got a conducting wire going this way, and then another one on the other side that you could imagine perhaps current going this way in one and coming back in the other. That's the old antenna wire that we used to use for our TVs. Your book has an example like that in it. I think it's the fourth example in the textbook. They actually work that out pretty well, and from that you can calculate the capacitance. That is in your book. They're only starting off with what we know about electric fields of cylinders. In other words, they're not doing the full paradigm. They're not using Gauss's law as the initial part to figure out the electric field. They're using the result that we already found, which is the electric field due to a cylinder of infinitely long cylinder of charge. Actually, I've went ahead and talked myself into doing it. Since the last example I did actually showed us using Gauss's law to calculate the electric field around a charged infinitely long cylinder, and we used it to find that the electric field was lambda over 2 pi epsilon naught times r. We should just be able to go ahead and jump from that step and ignore the Gauss's law portion. So I'm going to go ahead and do that as my next example. So let's begin. Here's another example. Now, in this example, what I'm going to do is imagine two little circles, if you will, because I'm looking at the end of this antenna wire that I told you about. And here is one circle, and then over here is, say, another circle. So each of those, by the way, will have a radius that I'm going to call R. So I'm going to just say that this radius and this radius are both just R, like that. So that's our radiuses of our wire. And I'm also going to say that the distance between the centers, so imagine a line here and a line here, and this distance from here to here is just D. And again, what I was saying it was like is they would actually have this metal encapsulated in sort of a plastic type material that became really thin here and went on like this, and then it had a little circle of material this way. Now, we're ignoring the effects of that, but in principle, you could include them. I'm just trying to give you an idea of what this particular cable looked like. Now, this is just us looking at the end of it. If you looked at it on the from the side, it would basically just look like this, where you could tell there was a wire in this part and there's a wire in this part. So that's really what this material would look like if we were looking at it from above or from below. And the second blue line, or the two inner blue lines, are supposed to represent the purple wire that I showed the end of above. So let's go ahead and do it. Our job here is to assume that one of these charges is going to have a value of plus Q. So I'm going to say this one has a charge of plus Q, and I'm going to say this one has a charge of minus Q. And the question is, what is the capacitance per unit length? Okay, so that's really what we're trying to calculate. I'm sort of doing the three-step paradigm, but the first step, which is where we use Gauss's law to compute, what I would do is use Gauss's law to compute the electric field on the leftmost wire. And that is exactly what we did in the last example when I did an infinitely long coaxial cable, because really I was using a Gaussian surface that was bigger than the radius of the inner cylinder, but not as big as the inner radius of the outer cylindrical shell. So it was basically just treating a single wire, just like we did in chapter 21 with Coulomb's law. So that formula should be identical to the formula for the other one, but the formula for the other one would actually have the electric field pointing inwards towards it. So the right wire, the wire on the right, actually has the electric field lines pointing towards it, which I could represent, for instance, by these little green arrows. Uh, and this one, of course, would have the electric field pointing outward, because it's a positive charge. And remember, the electric field direction is the direction in which a positive charge feels compelled to go. So that's what we're going to get. So step one, I'm going to say first off solution. Step one was use Gauss's law, closed integral E dot dA equals Q enclosed over epsilon naught to attack one of them. And from that, we would get, like we did last time, E is equal to lambda over 2 pi epsilon naught R. And that would point in what I called rho hat, because this would all be uh, basically in the plane of the page that I have here. It would not extend into the page or out of the page, which would be my z hat direction or my z direction. So I'm imagining the z axis going directly into the page, for instance, and this rho hat would point in the direction of the green arrows around the leftmost conductor. So that's the actual electric field that I got using Gauss's law in the previous example. For our case, this is going to become uh, the sum of the two. So the electric field, for instance, uh, between the wire on the left and between the wire on the right is going to be the sum of the electric field due to the wire on the left plus the electric field due to the wire on the right. So the way I write that is I'd say the electric field, and I'll leave it off the vector part right now and see what might be nice to write it. I'm still going to go on the assumption, for instance, that X and Y is the plane we're working with, so that maybe Y is the upward direction going from the leftmost wire to the word example, and then the X-axis would go from the center of the leftmost wire to the center of the rightmost wire, and then continue on past it. So in using that, I might wish to call the distance away from the center of the leftmost wire, I might wish to call that X. So that's what I'm going to do. And therefore, in this case, I would get Q over or actually let's say, I would say lambda times L, which is really just positive Q for a given length. So right now I'm imagining, for instance, just looking at a length L of the wire. So the leftmost wire would create an electric field given by, oops, I shouldn't have the lambda up there, excuse me. I shouldn't have the L up there. It should just be lambda, which I can write as Q over L. That's what I'll do. That'll be a little nicer. Sorry about that. You can tell I decided at the last minute to do this. So lambda is actually going to be Q over L, and then I get 2 pi epsilon naught, and the distance from the center of the leftmost wire to a point between the two wires is going to be called X, and that electric field due to the leftmost wire is going to point in the I hat direction. Again, with what I stated as my x-axis, as if it's going to the right. Let me go ahead and draw that in here just to make it a little more clear. So I'm going to use red so it stands out a little better. But that's my x-axis, say, and that's my y-axis. So this point right here is a distance x from the center of the wire. That's why I use the electric field due to the leftmost wire as Q over L 2 pi epsilon naught X I hat. So now I can go ahead, since I have decided to make it an electric field as a vector, and I've now got that one that points to the right. Now the electric field due to the rightmost wire also points to the right, so that quantity will be plus lambda, or excuse me, plus Q over L divided by 2 pi epsilon naught. Now this distance from it is, since the whole thing is d, it would be d minus x. So I'm going to say this distance is d minus x, and this should be reminiscent of what you learned in Algebra 1. It was probably the first thing that confused you. If you ever had any confusion in Algebra 1 in high school or wherever you got to take it, this would have been the first thing that confuses a lot of people. I know it was the first thing that got to me. Probably the first out of the 4 times I ended up having to take it because I was such an awesome student. So this one also points in the I hat direction like that. So now I have the electric field. Step one has been taken care of. Notice I am saying step one has been taken care of because we again used Gauss's law last class to calculate lambda over 2 pi epsilon naught r for a infinitely long cylinder of charge. So now I have the electric field. Now I need step two. Remember, we also have step two is delta V equals negative integral E dot dl. And then we have step three is C equals Q over V. So step two, we can go ahead and start. Step two says delta V equals the negative integral E dot dl. I just computed the electric field, and I am going to actually compute it from basically the left edge of the rightmost wire to the right edge of the leftmost wire. Now, listen to that wording again because I know it's pretty intense wording. I'm starting at the leftmost edge of the rightmost wire and integrating to the rightmost edge of the leftmost wire. In other words, I'm integrating from x equals d minus r to x equals r. So that's what we're going to do. Last time I did use the DL to indicate direction. I think I might use the range of integration this time to indicate direction. So I'm going to write down E, or excuse me, negative integral, and we are going to integrate from, as I said, D minus R to just plain R, because X would literally be D at R at the leftmost circle's rightmost edge, at the leftmost conductor's rightmost edge. So now I've got the range of integration as indicated. So the electric field is, as you said, as you can see, it's going to be basically Q over L over 2 pi epsilon naught times, in this case, we're actually going to have 1 over x plus 1 over d minus x, all that in the I hat direction. And now, since I used the limit of integration to show that I was going from right to left, I'm just going to put the dl in the positive coordinate direction. So I'm going to call it dx I hat, like that. And we're really staying in the along the x-axis, so we don't have to worry about the difference between rho hat and I hat, or rho hat and j hat, which it could also be in some instances. So this should all take care of it. This gives me, in fact, q over L is going to come out in front along with the 2 pi epsilon naught. Uh, I'll say the negative is coming out as well. Now I've got the integral d minus r to r, and it's going to be 1 over x. And actually, I'm going to break it up as two integrals so that we can treat it. It'll be 1 over x dx times I hat dot I hat, which we know is just 1 because it's 1 just like r hat dot r hat and j hat dot j hat were. And then the other integral is plus integral from d minus r to r, and this one's going to be 1 over d minus x dx. That one's going to require a little substitution. That's why I decided to change them. The substitution will be let w equal d minus x, which implies dw would equal negative dx. So I can just flip the sign and that will take care of that. So now I continue on. I'm going to say equals, I'll keep the negative q over L over 2 pi epsilon naught. And now the integral of x to the negative 1 dx is the natural log, and it'd be the natural log of r minus the natural log of d minus r, but that's the same thing as natural log of r divided by d minus r. So that one's going to be natural log of r over d minus r. And now I have a minus symbol that's going to come here with q over L over 2 pi epsilon naught. I didn't have to break it up this way, but I did because now I have a sort of a pseudo negative I can work with to change the dx to a negative dx. So now it's going to be the integral of omega to the negative 1 d omega, but in making that d omega into d omega, I had to change this minus to a plus. So there it goes. I just changed this minus to a plus. And this one, of course, is going to give me, we already have a negative q over L over 2 pi epsilon naught. That's actually going to be for both of them. But now what we've got is the natural log of r over d minus r, and then plus, in this case, we get the ln of w, which is the ln of d minus x. And then I've got to evaluate that at, again, d minus r and r. So when I do d minus x evaluated at r, it becomes d minus r. And when I do d minus x evaluated at d minus r, it becomes d minus parentheses d minus r. So this one's going to give me the natural log of, as I said, the first one was just d minus r, but the bottom one's going to be d minus d minus r. So obviously I've made it kind of tight. you should be able to read that that is d minus r over d minus r. What you see is going to happen is that negative in front of the parentheses d minus r is going to make it d minus d plus r. So the d minus d is going to disappear, and I'm going to get just an r in the bottom. So what we end up having is the sum of two natural logs. One is d minus r on top and r in the bottom. The other one is r in the top and d minus r in the bottom. So I can go ahead and write this as negative q over L. Again, that's just our stand-in for lambda over 2 pi epsilon naught times the natural log, and I'm going to put this in brackets, the natural log of r over d minus r plus the natural log of, now hold on a second here, I want to make sure I haven't lost a sign. I made it plus when I turned the dx into d omega, so that left it as a plus out there. And in order for it to have a negative out in front, I think I actually have to, yeah, let's think about that. In order to make it the plus out in front, in other words, when I distribute this negative q over L divided by 2 pi epsilon naught to both the terms, that negative is going to attack the plus between these two lens and make it a negative. I need to make sure I accounted for that. So what I was thinking of writing was just blindly go ahead and writing down the results that I got, which was d minus r over just plain r, like that in the brackets. But I want to make sure that it's acceptable to do that in light of me having a positive. So when I pulled out, for instance, this negative q over L, I didn't think 1 second. Oops. I didn't think 1 second about what was happening there, so I'm not sure that that is reasonable to do. Uh, and in fact, it might not be. So let me think about it just a second here. Uh, Yes, that should be a minus when I put it there. So let me go ahead. I'm going to fix that right now. So I'm making it really big. Remember, it had a negative in front of it, or it had a positive in front of it before. But then when I factored the negative q over L over 2 pi epsilon naught out, that should have been made into a negative. So that's right. That means this is a minus. And since that's a minus, now we're actually getting, instead of multiplying d minus r over r times r over d minus r, we're actually dividing by it. So what this is going to become is negative q over L over 2 pi epsilon naught natural log of r over d minus r. That's for the left term, divided by d minus r, oops, over r, and that's for the right term. Now, that just basically gives me d minus r squared and the bottom and r squared in the top. So when you take the natural log of x to the a can be pulled out in front, and that's what I'm going to do now. So when I do this, it's going to become negative q over L over 2 pi epsilon naught times the natural log of r squared over d minus r quantity squared. As I said, when you take the ln of something raised to a power, the power can just come out in front of the ln, and that's what we're going to do now. So that 2 will come out and it'll cancel out the 2 in the denominator here. So these 2 become a coefficient of 2 right here, and that 2 right here cancels out this 2 right here. So our final answer for the voltage in this case, at least without making any approximations or anything, is negative Q over L divided by pi epsilon naught. times the natural log of r over d minus r. And normally r is so much smaller than d that you can pretty much ignore it. Uh, in this case, yeah, you could definitely do that. And in order to change that from a negative to a positive, I could just flip the uh, I could flip the fraction in the natural log, because the natural log of x is the negative of the natural log of 1 over x. So finally, I get q, and I'm going to put the L in the denominator this time, over pi epsilon naught L times the natural log of d, and this is approximation because basically I'm saying, hey, d is way bigger than r, let's ignore r in that subtraction, and this is going to become d over r. So that is ultimately our voltage difference between the left edge of the right wire and the right edge of the left wire. So step 2 is now done, and step 3 is next. Step 3 is applying C equals Q over V, and that becomes Q divided by Q over pi epsilon naught L times the natural log of D over R. You can see the Q's cancel out again like they're supposed to. Remember, you're never supposed to have a Q or a lambda or a sigma or a rho in a formula for capacitance. It's all supposed to be geometric. So now I see that those cancel out, and ultimately we get that the capacitance per unit length. Well, let me not do that step. Hold on a second. Now I get that the capacitance is, the denominator has a fraction, and I got to flip that over. So that's going to become pi epsilon naught L divided by the natural log of D over R. So that's the capacitance. If I want the capacitance per unit length, I can divide both sides by L, and therefore I'd get C over L equals pi epsilon naught divided by the natural log of D over R. And that's it. That's the total capacitance for this antenna wire. Again, if my students were here, I would ask anybody if they have any questions. Feel free to ask me questions on my YouTube video, on my YouTube channel. You can just post it right there at the bottom of this video. I'll get an email about it, and then I will post the answer right there. So feel free to do that. Well, that is the last of the examples, working on examples like the ones your book has. That's the last of the examples of basically calculating capacitance. Now, what we need to do is focus on some of the other things we deal with capacitors. So, for instance, you might not know what actually happens when I connect a battery to a capacitor. So I'm going to do that by showing you what the formula for the equivalent capacitance is when I have any number of capacitors in series or when I have any number of capacitors in parallel. So that's our next step. So let's talk about capacitors in series. Now, you got to pay attention to the words I'm saying here so that you'll get an idea of what actually happens in the circuit when you connect it. But what we're going to take right here is I'm going to go ahead and show you the symbol for a battery, which we already know. That's the positive side, that's the negative side, and I'm going to say that voltage is V sub 0. And I'm going to imagine a wire coming from it and then going up to here, and then go a little ways, and there will be a capacitor of capacitance C1, and then there will be another capacitor of capacitance C2, and then there will be another capacitance of capacitance C3. Now, when we do this, what we'll discover is that we get an answer that's easily extendable for any number of capacitors, as you'll see. It just adds a dot dot dot, and we'll have it an ellipsis, in other words. Okay, so what we're trying to do is find a single capacitance that we could connect in the same circuit, and then if the battery was a prescient being, for instance, it wouldn't be able to tell the difference unless it, walked over there and saw that it's not two, not three capacitors, but one. So we want this to be equivalent to basically a battery voltage V0 connected to a single capacitor, and that single capacitor has a capacitance C equivalent sub S. And the S, of course, is just for series. So that's what we want. Now, if we are thinking about what's happening when I first connect this capacitance, let's take the rightmost circuit because that's just a single capacitor. So what we're imagining here is the fact that you connect this voltage up to a capacitor is going to the battery. Actually, I meant to say connect it to a. This battery is going to be connected to a capacitor. What we're going to see is the positive side of the battery is going to compel the free. We're imagining again what we call conventional current, that positive charges are moving around. So we're going to imagine that this positive terminal of the battery is going to compel all the positive charges to run away from the positive side of the battery. And in fact, what we're going to get is an amount of charge Q that's going to flow around. Now, as this Q runs into the positive charge, or excuse me, runs into the capacitor side, it's going to build up a positive charge on the left-hand side. And there's nowhere for the charge to go, so the total charge on the capacitor is going to be Q. Now, that's positive Q on this plate. Now, because of those positive charges, they're going to compel all the free positive charges in the right plate to run away. So this top positive charge is going to create a top negative charge, and then another negative due to the second one, another one due to the third one, another one due to the fourth one. So this guy's going to have a charge of negative charge. And then all those positive charges that were run away from the left-hand side, making them leave the right hand side, those are all going to return to the battery. So that's what happens. Now, it takes a little time, and in fact, we know exactly how much time it takes because it turns out if you multiply the resistance of this wire, or if you had a resistor in there in addition to the wire, it'd be the resistance of the wire plus the resistance of the resistor. If you take that resistance and multiply it by the capacitance of that capacitor, you'll get something that comes out in units of seconds, and it's usually on the order of micro or milliseconds or something like that, and that shows you that this would happen on the order of milliseconds, obviously, or microseconds or something like that. It might even be nanoseconds, but the main thing is you know that it's going to take a small amount of time, but still it's going to take some time. Now, if we look at the same scenario on the left-hand side, the battery, the power source shouldn't know any different either way. So it's going to say, hey, a charge of plus Q went this way, and that built up a charge of plus Q on the left and a minus Q on the right, and it made a voltage difference of V1 on this capacitor. And we know it's a voltage difference because remember, C is equal to Q over V, so that V is equal to Q over C. Now we see that Q is going to be the same as Q that left the battery because there's no other places for the Q to go. So the Q is definitely going to be the same for C1 as it was for C equivalent S, but because the C1 is different, that's going to make the V1 be different. So again, this is just going to build up a number of positive charges on the left-hand side of the first plate. Let's say only two in this one, and that's going to compel the right plate to become negative, and that's going to compel the left plate of C2 to become positive, and maybe that one's making 3, and that's going to compel the right plate of C2 to become negative, and maybe that's 3. And again, this is going to be the exact same amount of charge, plus Q minus Q. But again, it's going to get a voltage difference of V2. Now, again, that little piece of wire, let me draw over it again to see what, so you'll know what I'm talking about. This piece of wire, that left-hand side of capacitor C2, the piece of wire connecting it to the left-hand side of capacitor 3 C3. So I'm saying the right plate of C2, the wire connecting the right plate of C2 and the left plate of C3 was initially uncharged. It was neutral. But because it built up negatives by scaring away the positives, it's still going to remain a net charge of zero. So the exact same amount of charge should come up over here. And in fact, the idea of me drawing two and then three and then one or something like that is apocryphal because, in fact, it all has to be exactly the same. So we're going to get a charge of plus Q on the left side of each capacitor and a charge of minus Q on the right side of each capacitor. But what will change is the individual voltages. So we'll have a voltage V1, that's the voltage across capacitor C1. We're going to have a voltage V2, that's the voltage across capacitor C2. And we're going to have a voltage C3, or excuse me, V3 across the capacitor C3. Because of this and our knowledge of voltage, we know that the voltage right to the left of the power supply, I'm going to use one of my little bubbles and I'm going to use green this time. So if I actually took the the black connector from my from my multimeter, the COM one, okay? So this is a multimeter and it's set to measuring volts like that, and it has a V omega port, and then it also has a black port that's called COM, meaning common. Okay, what we're imagining here is I am taking this green wire and I'm connecting it to the positive V omega port of the multimeter. And then I could imagine connecting the COM to either the negative side of the battery, or I could just stick it in the little mouth hole looking thing, the little circular part right here. So, for instance, if I held it this way, that little part or that little part is the ground for a light receptacle. So it would be the same thing either way if I connected the ground or the COM to the ground or the COM to the negative side of the battery. So I'm going to go ahead and connect it to the negative side of the battery like this. Now, if I did that, the multimeter would read V0. Now, if you're ignoring the resistance of the wires, then it would also be the case if I had connected the left-hand side of C1 to the V. In other words, the voltage right to the left of C1 is V0. And since the voltage across C1 is V1, then it should drop from V0 to V1 on the right-hand side of C1. And it'll still be V1 when it gets to the left-hand side of C2. Then after it gets to the right hand side of V2 of C2, it'll have dropped another voltage V2. So now it's V0 minus V1 minus V2. And then if I go from the right hand side of C2, it's still going to be at the left hand side of C3. It's going to be a voltage of V0 minus V1 minus V2 still. But now if I go to the right hand side of C3, the voltage is going to be V0 minus V1 minus V2 minus V3. And we also know that that has to also be equal to zero. So we could plug it right here and say this is 0 volts. We could plug it right here and say this is V0 volts. And then, like I said, to the right of C1 would be V0 minus V1. To the right of C2 would be V0 minus V1 minus V2. And also to the right of C3 would be V0 minus V1 minus V2 minus V3. Okay. But that also has to equal zero. So what we get is that, and again, I should stop using green now that I'm done that. Uh, we would get V0 minus V1 minus V2 minus V3 is equal to zero, or more succinctly, V0 is equal to V1 plus V2 plus V3. which we should have known already because we did learn that whenever elements are in series, their voltages add to give the voltage of the power supply. So that's what we're saying here. Now I can use C equals Q over V in this format to actually elucidate that V0 equals V1 plus V2 plus V3. When I do that, what I get is looking at the rightmost circuit, I can see immediately that V0 is equal to uh, Q divided by C equivalent series. So I'm going to write Q over C equivalent series is equal to Q over C1 plus Q over C2 plus Q over C3. So now we have the formula. Obviously, there's a common factor of Q through all of that, so I can cancel that out. That's the whole reason I went through that long explanation of how the charges would act and going from one capacitor to the next to the next. So our ultimate formula is finally 1 over C equivalent in series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And I will box that off, and that's our equivalent capacitance formula. Now that is for just 3, but for any number you can see that I just keep adding reciprocals of the capacitance. Now, this is just like the formula for resistances in parallel that we learned in lab. So you should see that the resistance in parallel acts just like a capacitor in series. And what we learned about that formula was that when you put any number of capacitors in series, then the total capacitance will be smaller than the smallest one. So let's say you put 4,000 capacitors in a series and plug it into a battery. If the smallest one was 1 microfarad, then the total capacitance will be less than 1 microfarad. That's kind of a big deal, right? That's a really big thing, and that also tells you how you build different amounts of capacitance. So, for instance, if you only had a 100 microfarad capacitor and you needed a 50 microfarad capacitor, you could put 200 microfarad capacitors in series, and that would make 1 over 50 plus 1 over 50 gives you 2 over 50, and that's equal to C 1 over C equivalent. So C equivalent becomes 50, or excuse me, 1 over 100 plus 1 over 100 equals 2 over 100, and that would make 1 over C equivalent become 2 over 100, and therefore C equivalent would be 100 over 2, or 50. Okay, now let's do capacitors in parallel. So I'm going to say capacitors in parallel. So I have a similar drawing as I had before. I'm going to say this is my V0, and I'm going to go up to here and say this is C1. I'm going to go up to here and say this is C2, and I'm going to go up to here and say this is C3. And then all these wires will come back and come back here. Now, that's our uh, capacitors in series, and I want to make this equivalent to the following circuit, which would be just a V0 connected with a single capacitor, and that single capacitor would have a capacitance of C equivalent sub P. Okay, now in this case, what we're going to see is a charge Q is going to come out and then go that way and build up on the left-hand side. That's going to compel the charges on the right-hand side, the positive charges, to run away, and then they're going to come back and enter the battery as a charge Q, and no charge will be lost. In order for the left circuit to be equivalent to that, then we know for a fact that the amount of charge Q should flow out of the battery. But once it gets to this particular junction right here, the charges have a choice. Some fraction of them will go to C1, and then when it gets up here, another fraction will go to C2, and then anything that's left will go to C3. So what we're going to get here is basically a charge Q1 going on this capacitor, a charge Q2 going on this capacitor, and a charge Q3 going on this capacitor. And then, of course, that would cause the charge Q3 to leave it, charge Q2 to leave this one, and charge Q2 to leave that one, so that ultimately I have a charge Q returning. That tells us, in fact, that Q has got to equal Q1 plus Q2 plus Q3, and that's just conservation of charge. Or you can look at it and say, well, where else would the charge go? And that would be your answer. Now, that is what we found out about them being in parallel. So now what I'm going to do is use the capacitance formula as I have here, but I'm going to use it to solve for instance for Q. And in that case, Q is going to be equal to C times V. So I'm going to use that, and I'm first going to use it for the right-hand circuit. And when I do that, I'm going to get Q, the charge that actually leaves the battery, V0, has got to be equal to C equivalent sub parallel times V0. And of course, that also means that we can write it over here. So I'm going to say C equivalent parallel times V0 is equal to C1 times V0. Notice it's actually C1 times V1, but we learned in lab already that when you connect things in parallel, then the voltage across each of them is all the same. And since there wasn't anything but the capacitors in parallel, the voltage across the capacitor will be exactly the same as the voltage across the battery. So C1 V0 plus C2 V0 plus C3 V0 is our actual equivalent statement of conservation of charge. Now we can see that the V0 is common to each of them, and we can go ahead and divide out the V0, and we'll get this formula: C equivalent in parallel is equal to C1 plus C2 plus C3. And of course, if it was four, five, or six of them, no matter what number, we would just keep adding terms. So that's what we can see here is we just keep adding terms, and that's our formula for the equivalent capacitance of three capacitors in parallel. Now, that is two formulas, or those are two formulas that we'll use repeatedly in this chapter. Our time for the class has run out. I'm going to ask all of you guys to keep an eye out. I'm going to make another series of videos either during class time, but hopefully before we meet next week, where I'll work using these individual formulas on a system of capacitors, just to give you some examples. I would normally like to fit that in the class time, but I was really trying to take my time explaining this three-step paradigm and all the little nuances of it as best I could. So I use a little bit more time than I would normally have chosen to use, but I'm hoping this will help everyone. So feel free to send me questions if you have them. That's it. Thanks everyone for coming. I appreciate it. Normally I would just say I'm gonna wait here till the last person leaves in case anybody has any questions, but nobody actually came, and we also didn't have any people come to office hours this time. So that's it. I'm gonna stop sharing now and tell everybody bye bye. Younger's out.